Okay, Mr. Benson here again with the last of the solutions for the practice exam. So this is light and matter. Starting off with question 18, so we're told about a photon which has a certain amount of energy and a certain wavelength. We're told that electrons can exhibit wave-like behavior very similar to these photons. And what is the de Broglie wavelengths of these electrons? And this is one of those questions which is more or less a trick question, because the whole point here is that it is the wavelength that determines the behavior being similar in terms of diffraction and things like that. So if the electrons behave in the same way as the photons, they must have the same wavelength as the photons, and that could be written as it is in the question, or you could also write that as 200 nanometers. Either of those would be fine. What is the momentum of one of these electrons? Okay, so all you have to do here is use the formula that relates the wavelength and the momentum. So for a particle, that is P equals h over lambda. So we just put the appropriate values in there. Now, when we're working with momentum and things like that, we have to use the SI units, which are joules. So the Planck's constant we use is the 6.63 times 10 to the minus 34, that value. And this is divided by the wavelength, 2 by 10 to the negative 7. And we end up with 3.3 times 10 to the negative 27. What is the energy of one of these electrons? Okay, so this is another case where we're dealing with particles, not with photons, so we can't use those E equals HF or E equals HC over lambda equations. We have to first figure out the velocity, which is the momentum over the mass. We just worked out the momentum, so that's 3.3 times 10 to the negative 27. The mass of an electron from your formula sheet, 9.1 times 10 to the minus 31. And this gives us a velocity of 3643 meters per second. Then we have to work out the kinetic energy of a particle, which is half mv squared. So all we've got to do there is sub in our values from the velocity here, the mass, we again, same one from the formula sheet, 9.1 times 10 to the minus 31 times 3643. Make sure that you square the velocity, that's a mistake that people often seem to make, and we end up with 6 times 10 to the minus 24 joules. Okay, so moving on now, we get to a photo emission experiment. So we're thinking about the photoelectric effect in this one. We're given quite a bit of information about it. We've got the graph and we've got the diagram itself. The diagram's pretty generic really, even though it might be drawn slightly differently. Okay, what is the maximum kinetic energy of electrons ejected from plate M? Give your answer in joules. Now, this graph is showing us here is as the voltage is adjusted in the circuit, this is what's happening to the current. Now you can see down here that your when we've got a 1.5 volts, then we have no current flowing, so this is our stopping voltage. So that corresponds to the maximum kinetic energy. So in this case, when we go down here, we know that our maximum kinetic energy is 1.5 eV. Now the only thing we have to do here is convert this to joules. So the calculation there is to multiply it by the charge on the electron, 1.6 times 10 to the minus 19, and our answer for this one is 2.4 times 10 to the minus 19. So 2.4, make sure you write your answers in the box. Okay, the light source used in the original experiment is replaced by 1 or twice the intensity but of the same frequency. The experiment's repeated. Draw on the current voltage relationship for the second experiment. Okay, so this is one that asks us to understand the photoelectric effect, and in the photoelectric effect the intensity of the light is the number of photons that are striking the surface, and so it will affect the current. Each photon though has the same energy, so it's not going to cause photoemission to happen any sooner. So the stopping voltage will be the same. So our graph will start at the same point. Because the intensity is double, our current is going to be double. So we want a nice straight line there. Sorry, it's a little bit hard to draw on my computer. And the line here will go from 0 up to that other point in a fairly straight line when my computer decides to behave. Something like that. So that would be a reasonable answer. Now we're asked to explain this in terms of the photon model, so we need to explain this reasonably well. It's a 3-mark question, so 1 mark is probably allocated to the line, so we've got 2 marks about the that we need to say in our explanation. So one of them that you could say is that the stopping voltage or the max kinetic energy depend on F, not on the intensity. And remember that the photon energy energy is dependent on the frequency, E equals HF. And the other point here in terms of our explanation is that the current is, actually I should say intensity up here rather than I, because that's getting confused with current. And this is probably not going to work for me. So the current is proportional to the intensity, as the intensity is the number of photons. Okay, so those two are reasonable points to address that question. Moving on, light incident on a smooth surface is reflected with an angle of incidence equal to the angle of reflection. Select which one of the following statements is true. Can be best explained by the wave theory of radiation, can be best explained by the particle theory of radiation, explained by both, or not explained by either. Now this is one that is explained by both. We can easily explain reflection in terms of either theory, so C is correct there. Okay, moving on. So now we've got to start thinking about the way electrons behave in the shells as they absorb or emit energy. So a simple hydrogen atom has been excited from the ground state to the second excited state. So the question is, what are the possible energies of the photons emitted as the electrons return to the ground state? Now, what you've got to remember here is that we've got a number of options. The first one is that it could drop all the way in one transition. The second one is that it could drop in one step and then another one. So there are actually 3 answers here for this 2-mark question, which is slightly weird. So 12.1 is one, 1.9 is another, and 10.2 is the third one here. So those are the 3 possible transitions. Okay, what is the energy of the shortest wavelength photon that can come from the hydrogen atoms as the excited atoms return to the ground state? Now what you've got to remember there is that short wavelength is high energy. So low wavelength is high energy. So when we look at our transitions up here, the 12.1 electron volt transition is going to be the energy that we're looking for in this question. So then we get to what is the shortest wavelength of the photons, and so what we've got to do is take our previous answer and just find the wavelength from that. Now all we need to do is go lambda equals hc over E. Now we just need to use the appropriate value of h because we've got our energy in electron volts, so that's 4.14 times 10 to the minus 15 times the speed of light. And we get 103 nanometers. Okay, moving on to question 22. So this is a double slit experiment question. We've got now, for some reason I didn't like this question, but I'm not quite sure why. Okay, so we've got red light being shone through the double slit, and we're getting the diffraction pattern forming that we'd expect. With everything else kept the same, the red light source is changed to a blue light source. Describe the effect of this change on the pattern seen on the screen. Now I can't quite remember why I didn't like this one, but the important thing is that blue light diffracts less, so that will make the fringe spacing smaller. I think that's a reasonable answer for that question. And lastly, describing whether we think the particle or wave model for light best explains our answer to part A. This is basically explaining why Young's double slit experiment supports the wave model. So we need to talk about diffraction and how it depends on the wavelength. We need to talk about constructive interference. Excuse my weird scribbly writing. So constructive interference occurring when the path difference is in multiples of lambda. Something like that. Okay, so that's the end of the light and matter section. I will work through the sound one shortly.